Hey everybody, welcome back to the channel. Steve, Short Shift Garage. So, I put up a video yesterday regarding coils and timing and things like that. And I took it down shortly thereafter because it greatly oversimplified it. And I realized later that it could lead you in the wrong directions and that there were some things that really didn't make any sense from an engineering standpoint, and some of you guys are so super critical that if I make a mistake I get called out immediately, and rightfully so. So what are we going to talk about today? Well, same subject as the one I did yesterday but have deleted now, and that is we're going to start off with ignition coils. So we know we all have 8 ignition coils in our vehicles, and one of the things I constantly see is people who have gone out and bought aftermarket ignition coils thinking that they're going to improve their performance. And the reality is that it's not probably going to happen. There has been one study of someone using the MSD blaster coils that are available out there, the pretty red ones. They look cool on your car, but really they're just digging money out of your wallet. But this study said the guy gained 10 horsepower, or roughly, and it was done by some college. And I have no proof that the college actually did it. They did it on a Charger 5.7, and I don't know who paid for it. Okay, so it seems far-fetched to me, and so I'm taking that one and throwing it away because I just don't believe it. So let's talk about our OEM coils. First of all, after 2014, or up to 2014, they used one coil, and they changed the coil in 2015. I don't know if they changed it because they changed manufacturers, or whether it was some engineering move that required the change. We do know that the 2015 through 2023s is the revised version, and there's a couple of revisions in between there too. But if we consider the fact that from 2015 on, that coil has not changed, and it's the same coil used across all of the engines. Okay, it's used in the 5.7, it's a 6.4, it's in the 6.2s also. So it is adequate for boosted applications. Up to what the Hellcat uses. I did not find any Demon 170 or Demon or Red Eye tune files to compare with, but if you look across the 5.7, the 6.4, and the 6.2, they're all using the same dwell. And that tells me that the output voltage from these coils is absolutely adequate to work across all these engines. Now, let's talk about spark. Okay, so you know your spark plug's got a gap in it, and you're told to gap your plugs to a specific number. That's both plug manufacturers' recommendations and Dodge's recommendations. If a spark plug requires a certain amount of gap, that tells us that we have to reach a certain voltage in order to cross that gap or break that gap down. And that gap is the equivalent of resistance, okay? And that's why we have it there. We have that gap not only to provide a spark, but to provide resistance so it doesn't trigger too quickly. So there's a couple of reasons that that gap is there. Now we move away from the gap subject. We know it's there. We know we have to jump that gap. We have to produce enough voltage and microjoules to get across that. But where's the key to this? And that's in that coil. So coils. Let me explain. I'll show you a graphic of a coil here. I'm going to switch to my desktop. And we'll get a picture of a coil up here. So this is your basic coil. This is kind of what ours look like. That would be a single output. Ours a dual output because we have 2 plugs per cylinder. But this is a traditional coil. And you can see it has some windings here. And the way it works is that we apply, a coil is basically dead. There's nothing in it until the either the points or the ECM tells it turn on the voltage. So when the points in a point ignition system, when the points close, that means that the coil is building its current and voltage. And the minute they open, it's a magnetic field where the charge exists in here, and it's stored in there. And the minute you open it and remove the voltage, that magnetic field collapses at a certain rate. And when that happens, the energy stored here is released, and it goes out through the top of the coil. And that, of course, goes to your plug. So it's going to get released here, and boom, it goes out. It goes out here, it goes to your spark plug. It overwhelms the gap, and you produce an arc. And that's kind of the basics of it. Now, what controls how much voltage is stored here? And that is what is known as our dwell. And if we look at our dwell, we will look here, and I'm going to go, both these tables are the same, but they're internally different to the PCM. So it's a little bit different. I'm just going to pick one to explain it, because I do not have the algorithmic logic behind when it switches from low to high and for what reason. So I don't know. Here we're looking at, let's just take 13.5 volts. Now I know our engines run more up 14.2, 14.3, somewhere in there. But we're going to use this 13.5 volt because if you interpolate this and rescale it, you can break it down further. But for the purposes of this training, we're going to use 13.5 volts. And that is 2,816 microseconds. Think about that. Think about how fast it can reach its designed output voltage. Now, we're saying designed, and there's 2 different levels for output voltage. If you continued to allow this to build, it would, so in other words, if say we went up here at 7.5 volts, it would take 6,000 microseconds, 6,016 microseconds to build to the potential that we want. But more importantly, if we modified this and it extended, it would produce a higher voltage up to the point where the coil became saturated. Now, the one thing we want to avoid is coil saturation, because it's kind of like knock. If you think about it, it can destroy that coil. You'll generate way too much heat, and in a very short period of time, that coil will just trash out and be gone. It just destroy itself. So what the engineers have done is they've said, okay, how much how many joules, how much voltage do I need to break down that gap in that spark plug and create an arc. And so the coil was designed around that, saying that I want this coil to last. I want it to last as long as the engine lasts. So let's just say they want it to last 100,000 miles. We're going to use that for reference. Yes, you can get more than 100,000 miles out of a coil. But from a reference purpose, we're just going to say 100,000 miles. So the engineers said, hey, if we run it, if we only need this much voltage and current to break down that air gap in that spark plug, then we only need that coil to produce this amount of voltage. Okay, we don't need it to produce more. We only need it to produce this much, and therefore that will put less stress and strain on the coil, and it will last longer. So it's interesting to note that this same coil again is used all the way through all the engines, identical part number, and that the dwell time, the amount of time it takes it to go from 0 to a stored voltage amount, typically it looks to be, and we don't have the numbers on this, okay, in order to do it I would need to build a test vehicle or a test engine system, and it's very expensive to do that. But build a test system and actually test the coil 100% using an oscilloscope. So I don't have that. I'm not going to do it. But we'll just say roughly we want this at 25,000 volts when it's done. And so if that number is the actual number that Dodge is trying to reach, they've said that's good. That's a good number all across every vehicle, every engine, and because they did not change this dwell time. They kept it the same across all the vehicles. I've got, I could show you a 2016 Hellcat, and let's just open that up real quick here. I believe we'll look at that same low energy dwell, and yeah, it's identical. Okay, identical numbers. So let's look at the RPM dwell. Okay, so RPM dwell on the Hellcat is at anything above 2,000 RPMs, it's 416. What is RPM dwell? Well, the closest we can find, or the closest guess, is that it's a buffer. It's a mechanical buffer because every engine is going to need some sort of mechanical buffer. It's like, say I had to have bearing clearance. Yeah, okay, you know you have to have some sort of clearance in that bearing for the lubrication. Let's just say that the engineers decided that at RPM, anything above 2,000 RPM, we need to have a 416 micro, and this is microsecond buffer in there. And HP Tuners defines it, I don't know if I can get it up there. Yeah, they define it as RPM dwell, or the dwell time adder for engine speed effects. So you kind of can get the idea where it's basically accounting for slop. But these numbers didn't change, okay? The 5.7 actually extends this a little, defines it a little bit closer. Let me open the 5.7 file again. Oh, where am I? And we'll look at RPM dwell here. You see the 5.7 is actually defined it's much finer, but it's still the same numbers. They just spread it out. And I'm assuming that's a difference in the PCM OS and the way it handles it. It's a little different handling of it. I don't know what that is because I don't have the algorithmic logic and nobody does. So we're guessing. Again, yeah, sometimes there's more guesswork than you think. But these numbers over here, the high energy dwell did not change. So these dwell numbers here, this is the charge time. So if you take, say, we're going to use this as an example, 13.5 volts. So it's 2,816 microseconds, not milliseconds, but microseconds for the basic high energy dwell. And then we add this on there for the slop. You're going to come up with a number that's 3,332 milliseconds, or microseconds, and we'll break that to milliseconds because it's a little easier. So that would actually be 3.232 milliseconds. So let's just say we use this number here at 4,000 RPM. And if at 4,000, this is a mind blower. At 4,000 RPM, the crankshaft moves 24 degrees per millisecond. And if that happens, that means that our dwell needs to occur at, if ignition happens at top dead center, which it doesn't, but we're using it for example, then our dwell has to start 77.568 degrees before top dead center. And the reason it has to start there is because when that ignition event occurs, that coil has to be at its desired voltage, engineered voltage. And because when you take the charge voltage away from that coil, the magnetic the magnetic field collapses and releases all the energy. So it needs to be ready for that firing event to occur. If it's not ready, you're probably not going to reach the voltage that you need to be at, the voltage and the joules that you need to be at in order to break down the gap with the spark plug. So, yes, dwell is critically important. Where it occurs is critically important. Now let's just say in our average engine at 4,000 RPMs, we're requesting 18 degrees timing. And that's 18 degrees before top dead center. And that's a typical timing number. So now let's look at when dwell needs to occur. Well, in that situation, it's going to occur at 95.568 degrees before top dead center. So if we say 95.6, that's a pretty reasonable number. How does it know? And that is because we have something called a crank sensor. And that crank sensor knows exactly what that crankshaft position is. Okay. The PCM, the crank sensor doesn't. The PCM knows exactly where that crank sensor is reading at the moment. It doesn't. We know we have a reluctor in there, and it has teeth on it. So that's all calibrated. How fast that the reluctor goes past the sensor. The PCM calculates that and breaks it down further and further and further, and knows exactly where that crankshaft is in its rotation, and therefore can precisely start the dwell process for that coil at the right time. So when that crank hits that position, the PCM knows to turn on the voltage. So it turns on that 13.5 volts. That 13.5 volts turns on for a period of 3.232 milliseconds. And we know that our crankshaft moves 24 degrees per millisecond. So at 18 degrees, we have to be at 95.568 degrees before top dead center. Before, and we have to be there exactly at the same time that our spark event is supposed to occur. We've requested 18 degrees. That's that whole dwell event needs to occur that far ahead of time in order for that spark to occur at 18 degrees. Okay, so it's not really that difficult to understand, but it's difficult for other people to understand how or why another coil, something other than OEM, is rarely a great solution. It's not going to save you, and as long as you're still operating, within the realms of the engine. And if you change the stroke of the engine, then where dwell occurs is going to need to change too, and possibly the length, the time of the dwell, the duration of dwell. So there you go. That's dwell in a nutshell. Now you're going to see people who they'll put up it's representative, I guess, of a degree wheel that you might use on your crankshaft, and you can actually put a pointer on that degree wheel and say, okay, this is where dwell is going to occur. But dwell is a moving target, obviously. We have tons of things going on in this engine that are affecting our timing. We may request 18 degrees, but it doesn't mean we're going to get it. There's a lot of other factors, and that's what makes That's what makes modern engines so amazing. And the level of engineering is just mind-boggling. Because timing can be, or is, I'm not going to say it can be, because it is a moving, living entity and determined by all sorts of environmental stuff. Intake air temp, intake manifold temperature, MBT, maximum brake torque, barometric pressure. All these things affect your timing. So obviously, the one stable thing we have is the amount of time it takes to charge that coil at a specific voltage. Wait, okay. What happens when our voltage starts changing on us? Well, it does. It does move around. And so this scale here is very loose. And of course, the PCM is going to break it down much finer than what is available here. These are just hey, these are benchmark locations, and this would be a benchmark at 13.5, but the PCM will say, okay, so right now we're at 14.7, so maybe this only needs to be 2, and it does the math internally. It will change it. It'll interpolate it and change it and actually give the correct dwell. So to say that this is exactly the dwell it's going to be in your engine, it's not. So you can't really graph it out in a degree wheel in the same way that you can plot out your camshaft. It's just, you can't do it. And so when I see these graphs saying here's where dwell starts, I just say maybe, because that's the only correct answer. You can't say it's going to happen there all the time, because it's going to change. It's going to happen somewhere in there, but you can't plot it out and say it's going to always happen in this exact spot or near or around this exact spot. It's going to happen, that, and it's going to be obviously on the compression stroke of the engine. So if you consider that happens, every 30 milliseconds, then it's a pretty phenomenal thing that occurs here. And it's amazing that these modern coils can keep up with it and can actually live as long as they do. So that's it. That's dwell in a nutshell. It's all, your coils are based on Faraday's law. You can look that up. It's inductance. That's your physical law. If you study electron theory, then you'll understand that. I didn't want to go that deep with it because I don't think we need to. But I did want to clarify how a coil works, how the induced voltage, or the voltage that's applied induces current creates a magnetic field where current is stored, and then once you release that voltage, the applied voltage, once you turn that off, then the field collapses and releases the energy, and that's what jumps across your spark gap. So spark gap's important. Don't play around with it. Do it right. You can adjust spark gap. And so, but you'll need to read the plugs. So a lot of people say, I want to see a mark on the strap, which is the ground electrode, or the ground, it's electrode. I want to see a mark on that strap halfway between the body of the spark plug and the tip of the strap. You can move that just by changing the gap slightly. Because if you open the gap up, you provide more resistance. So it's going to take more voltage. You close it down, it'll move in the other direction. So yeah, you can modify that. People say you do it with timing. No, you don't do it with timing. I see people saying, yeah, it's timing. No, that's not what happens. It's not the way it works. That strap is formed by the arc. And the arc is produced by the coil. And where timing happens, where spark occurs, that's where it is in the cylinder, but that mark is not produced. That mark is a result of the arc. Now, can fuel richness or leanness affect where that mark is going to land? And that's where people use the position of that mark as a tuning aid. It's not if that cylinder was nothing but dry air, you could land it easily by changing the gap. But what else affects the resistance there? And that's the fuel mixture. Yeah, sure. Absolutely is going to change the resistance. So the density of your fuel will in fact increase the resistance that's available, that's present at the gap. So if you increase that resistance, you're going to have to either fix that problem through tuning by getting your fuel back in line. If it's running rich or it's running lean. When the engine's running optimally at the prescribed fuel to air ratio, then the voltage that we have available in that coil is perfectly adequate to break down the resistance at the gap and produce an arc. If you start running very, very rich, it could take more voltage to break down that gap. However, these engineers are pretty sharp, and they're not changing the dwell because they don't need to. There is adequate voltage always there, no matter, well, if you go super rich, yeah, you're going to flood it out, and then it can't cross the gap. Just like, okay, so here's an example. Normally, I go out and I push the button on my little bulb on my weed eater. I push it 3 times because that's all I need on mine. It's well tuned. So I push the bulb 3 times. I have enough pressure in the tank to push fuel up. I pull the starter rope 3 times, 2 or 3 times, and it starts. Now, if I push it, the manufacturer's recommended 8 times, I'll flood it and it won't start. And so I have to either pull the plug out, blow in the cylinder, get some of that dense fuel out of there, and then I put the plug back in again, and now when I start it, it starts up. Okay. That's a pretty lame and rough analogy, but basically that's what can happen inside your engine too. So as the fuel density increases, the resistance across the gap is going to increase, and eventually if you increase the fuel resistance too much, the voltage that the coil is producing will not be adequate to create the arc. So that's on the rare side, and apparently with our Dodges, the way they're designed, you can run in normal operation. There will never ever be a time when we will have, with a standard tune, stock tune, that we're going to have too much fuel in that cylinder to overcome, for the coil not to be able to overcome the gap in the spark plug. Boy, I hope I said that right, because it's kind of like a mysterious subject to a lot of people, and you understand now when we start playing around with injector pulse widths, we're probably in the wrong area, okay? And we actually want to work with timing and air, because injector pulse widths are pretty well and easily defined by Dodge, and they work, okay? But there's a lot of tuners that'll go out there and they say, I'm going to modify the injector pulse width. And that throws every frickin' thing off. That's just ruins everything in the path. But I digress, and I'm getting off subject here. But I want you to understand, one, realize how fast all this stuff happens. I mean, we're talking microseconds here. And realize the one key is, here's one that's pretty evident. At 416, a camshaft, or the crankshaft is moving about 10 degrees during that time. And that's in microseconds. And I'm talking micro. We're not talking a second. We're not talking a millisecond. We're talking microseconds. So in 416 microseconds, a camshaft moves about 10 degrees. So get those things in your head and realize how fast everything's happening. And if you understand how fast everything is happening, when you're going to make changes in your tune, and you have that thought in your head, hey, wait a minute, shit's really happening quick here. A small change can be a ton. And that's where a lot of tuners go astray. They'll start making changes, not realizing how fast all this stuff is happening. And they'll make a what they think is a small change, and it ends up being a huge change. And of course, then they end up dumping a bunch of fuel in during wide open throttle and all this other stuff. And it just turns into a mess, and they can't understand why. It's because they don't realize how fast all this shit happens. So, I'm going to end it here. Let me go back to the desktop, to my webcam. There we go. So, hopefully, I've gotten into your head a little bit. And because now that we can see how fast everything in this engine occurs, and the best example is how fast a coil can reach its desired output voltage, discharge that voltage, create that spark, boom, ready to go. Okay? We now know or have a physical grasp on how fast everything happens and how small, subtle changes in your tune can be a lot more undesirable if you make them wrong than you might think. Every engine will wear differently. So every engine is different. Is there a canned tune out there that works on every engine? And the answer to that is maybe, but it's pretty sloppy. I know a lot of people buy the Diablo tuners because they believe that, hey, they come with canned tunes. I would say they're more like cartoons. Do they work? Yeah, you'll feel a little bit. Is it right? Probably not. Is it right for your engine? Probably not. Is it a waste of money in my book? Yep. I absolutely think so. But Diablo's been selling them for years, and there's a lot of satisfied customers out there, so I'm not going to tear down Diablo for meeting their customer satisfaction levels. But their customers obviously don't really understand what's going on. And you, as tuners, can't live life like that. You cannot. You have to understand what's going on in that engine when you're tuning it. And now you have a grasp on how fast shit happens in that engine and how much change can occur in such a small period of time. And that's why accuracy. When you're making changes, don't make big changes, make small ones. Creep up on it. You're saying to yourself, well, I got a dyno and the guy only paid for 3 pulls. Is that enough to tune this car right? Yeah, if you're a real sloppy tuner. You're tuning for the track. You're going to make 30, 40 pulls. If you're tuning for the street, you should be making 30 or 40 pulls. But most people don't do that, and because they don't regard a street tune as anything critical. When in fact, done wrong, it can cause excessive wear and tear in your car over time. So people say, well, I got this, I put all this stuff in my engine and now I only got 50,000 mile lifetime on my engine. It didn't have to be that way. It does not have to be that way. If you are a good tuner and you take the time to tune an engine with a good understanding of what's going on in that engine, you can basically make that car run and last just as long as any other car on the road that's completely stock. Okay? So, I'm going to end this here and call it good. And I'm hoping you all got something out of this. If it's just confusing and mind-boggling, you better hire a tuner. You better hire somebody else to tune your car and take on the responsibility. Alrighty, I'm going to let you all go at this point. You'll have a good time tuning your cars. This is Steve, and I'm out. Thanks. Like and subscribe. Bye.